So before starting today, I was this will be, I guess, the most difficult day in a sense of mathematics. There will be a lot of mathematical formulas. My goal is not to go through them. The idea is that I want to give you the background of everything what is happening behind the way how we calculate ice. So just to get an idea, the material presented today covers in an undergraduate studies 3 exams. System analysis, which is each of them a 1-term exam. Advanced signal processing, which is 1-term exam, and advanced statistical analysis, which is, in my case, it was 2-term exams. So I'm talking almost of an academic year worth of material narrowed down in 3 hours. It might be brutal, but my goal is not to give you huge details of what is happening under each equation. I will just glance over it. My goal is to give you a skeleton of what steps we are going through in order to analyze ice curves in such a fast way. I give all the references inside, and I expect from your side as a researchers not to believe me, because our core business is not to believe anybody and to test and recreate. So my slides today are just a skeleton where you can go through, and in each step, maybe you will have some unknown stuff, and you will have to go quite deeper to analyze it. So I completely rearranged my presentation in the last couple of days. I uploaded the new version on the repo. So today's presentation, I flipped it. So I'm going to start from the end. Why I want to do it? Because I want to show you the final result, which is rather small and compact. And then I'm going to show you all the mathematics, how we came to this closed version. Okay, so where we were yesterday, I said that we have a stochastic excitation that I'm going to show you today. How are we going to generate? We either put this excitation to the current or to the voltage, depending whether we are doing potentiostatic or galvanostatic excitation. We do some time frequency analysis we're going to analyze today. And these are the results. I'm going to go in depth. What do they mean? And finally, I'm going to show you today how are we calculating ice based on these chaotic images. And how can we do it fast and computationally efficient? And even more important, there were several questions yesterday regarding the noise influence. We are going to go deeper into that. So now first, the final results before going further. So the calculation of ice follows these 6 steps that you see in black rectangles on the screen. First, we have to generate our excitation signal. There is a Python function for that. I'm going to show you the code. The code is something like 6 lines. And there will be approximately 10 slides of mathematics that are showing how we are getting to those 6 lines. I put a lot of figures, so you have the equations. Don't be afraid of them. They're there for your reference. I will try to do everything in a comic book style as possible, so that I will be gentle. So we have an input signal and an output signal. The output signal is the thing that we measured from our system. So here below on this yellow rectangle is a schematic representation of our system. Let's discuss it. So this part here inside we call a theoretical system. So it is as if we have some sort of electrochemical system. The equivalent circuit model is just for information for the depiction. It doesn't assume any model. It is. I just wanted to say that this is some sort of electrochemical system in whatever source it is. And let us assume that it is ideal. We can measure it without any noise. That's the white part. The yellow part is the reality that we have around it. So we can generate a signal without any noise on our PC. But when we put this signal out to excite our system, Mother Nature unavoidably superimposes a noise on the input side. So our fuel cell system is actually getting our ideal signal plus some noise. And what comes out is system output of our true signal plus the noise. And on top of that, when we try to measure this output, Mother Nature provides an additional noise, which is called measurement noise. And these are the signals that we are dealing with. So we have input, which is true plus noise, and we are having the output signal, which is the true signal plus the noise signal through our system, and on top of that, another noise that is called a measurement noise. These things are inevitable. Whenever we measure something, Mother Nature imposes noise on top of it. And we have to deal with all these parts. To complicate the things further, the signal that we are putting is not a sine signal, but it's noise by itself. So this now becomes completely mind-boggling. We are just putting in all these schematics noise plus Mother Nature noise plus measurement noise and all this jibber jabber, and out of it we can calculate ice. This sounds rather strange and like an academic playground, but it actually works and it's quite stable, and we can even compensate for a lot of stuff. So why this part is so important? Because when we have such noisy stuff running around, we have to take really careful steps how to analyze it. And in this case, we are doing it with these two steps here. And this is how we calculate part of our ice. The Python code that you see in this rectangle here is everything that we need to calculate ice based on these noisy inputs outputs. These are, I don't know, 6-7 lines of code. And I'm going to use the majority of the time today to tell you all the mathematics that boils down to 6 lines of code, nothing more. And the beauty of all of it is that since we are constantly using stochastic signals, the output is actually a stochastic output, a random stuff. So our ice, what we are drawing, is the mean value, the most probable value. On each part of the ice, we are now capable of drawing a confidence interval. This means that for each frequency point, we can say the impedance is in this frequency point is this, and this is its distribution. This is just what we are drawing is a mean value. But now, today, I'm going to derive the distribution here. And why is this important? This is important then, let me see if I have more white space on the other slide. Yes, I will, wait. I will do it like this. I will add a slide where I can make whitey, like a small whiteboard. Why is this important? Because we are measuring ice like this. This is what we would like to see. But in essence now, because we are using stochastic excitation, for each frequency, we can have a distribution. So this is the mean value in real, and similar stuff will be in imaginary, a rather strange, a different shape of distribution. But what this allows us is that when we measure after some time, this ice will change a little, right? Maybe there was some degradation. And on same frequency, we will have a rather different point. And on this different point, we can now estimate the parameters of this PDF, and we will have something like this for the real and for the imaginary, mainly on the left side and on the right side. And since now we are dealing with PDFs, we can use statistical tests, stat test, to check whether these differences are significant or fall within our estimation noise. And because we can do this, we don't have to ever look at our ice curves with our own eyes. We can use simple statistical tests to check whether some changes occur. And because we know the frequencies of all these points, we can always actually draw stuff like this. We have a reference. Let's say the blue one is reference and the red one is current value. We can say there are no changes in this frequency region. There are changes here, no changes here, small changes here. And we can do graphs like this. And based on the changes where this frequency occur, we can do some fault analysis. And this will pop up automatically. So in order to disseminate all of this stuff, there is some mathematics behind it. We will go through advanced signal processing concept, advanced statistical concept, and statistical testing concepts. I'm going to provide all the required equations. Don't be alarmed by them. The results are really, really simple. So the most complicated part, where we are going to spend the most time today, and I think it will be the most difficult, are the way how we calculate all this stuff out of noisy signals. And after, I think, around 40 minutes of mathematics, it will boil down to 2 times Fourier transform and 1 time inverse Fourier transform. And this is implemented here. This is the first 2 slides are the actual last 2 slides of the presentation. And we'll go through 70 slides just to tell you that this is the result. I mean, if we were on a conference, I would have said, this is how you calculate it. Trust me, bye-bye. Are there any questions? And then you have to trust me that, how is this possible? We have a lot of noisy stuff. And he says that it's 5 lines of code. This is impossible. I want to give you all the details so that you can understand as much as possible. And you must not trust me nor anyone, so that you can recreate every step of this thing. It might be really difficult. As you can see me, I'm constantly in defense mode with my body language. I apologize upfront, but today is the last day with such a mathematical sausages. From tomorrow, there will be only figures. So, and the final thing is how we estimate the PDFs. when I'm going to show you the equation of the probability distribution of the impedance, it will cover the whole slide. It is enormous. And we have it derived in closed form. The funny part is, in order to estimate its parameters, we only need these three equations. And if I gave you this code here, it says multiply two coefficients and take its mean, and then this relation. And we'll say, where the hell does this come from? What's the meaning of it? This function is an implementation of these three relations. And I have to go through some mathematics to tell you that everything that you've seen down, only these three equations are important, nothing else. And if you trust me blindly, you will say, okay, fine, let's forget about those gazillion slides before. I trust that these three equations are correct. But that is not your core business. You must not trust me. Okay. Roadmap for today. You will see this slide over and over. And as we progress, I will change colors of this square, so you will know where are we currently. These parts are where we are going to, where I'm going to show you numerical implementation of all those mathematics that I already showed you. There will be no more than 50 lines of code, 50. There will be, I think that I have, there will be on bottoms of the slides, these two icons. The blue one is a diver that dives around mathematical expressions. If you find it difficult or whatever, you can doze off, go on Instagram, whatever you do. After a set of those blue slides, there will be a orange slide with a takeaway note. I will tell you, wake up. From all these mathematical slides, this is the final result, and the final result will be extremely simple. And if you want, you can go back on the blue slide and recheck it by yourself. So I will wake up the audience because I expect that some of you might find this rather lean and difficult and boring, but the orange slides will be the important ones. Okay, let's try and see how this will go. So yesterday we were talking about system identification, and our goal is to identify our electrochemical system. That is in electrical engineering terms. In let's say in the field of electrochemistry, this means that we would like to find the ice curve. That's it, in simple terms. So we said that we usually do it by putting sine waves, and each of these points corresponds to a different combination of input and output signal of the sine wave. This is rather simple because the sine wave is deterministic. Mother Nature will superimpose noise on it, but because it's a deterministic signal, it has high signal to noise ratio, which means that the power of the signal is much greater than the power of the noise, and we can more or less say that noise doesn't influence our accuracy. The disadvantages is, the main disadvantages are that we have to make a single excitation for each point on the ice curve. So, as I said, one step further is to use non-periodic signals. The advantage is that we have all frequency together. The biggest hurdle is that we have low signal to noise ratio because we are mixing our noise with Mother Nature's noise, and everything gets mixed up together. We cannot separate it easily. And in order to separate, we need to have advanced statistical and signal processing techniques. This is the biggest issue. So whenever you start in the field, you always go through the simplest, most intuitive way how to solve the problem, and that will be with sine signals. But if you somehow manage to go through the pain of learning these approaches, then you can just jump to more advanced techniques. And this is what I'm going to tell you today. Okay, so yesterday I put a slide like this, which I said on several occasions that no one does ice like this. But to be even more precise, the equation is wrong. But this slide embodies the way how we think we calculate ice. So we take a sine wave and we take a Fourier transform of it here, and we take the output. The output has the same frequency as the input plus some phase difference that was imposed by the system. We calculate FFT of both of them, and we take a ratio. There is a really major flaw in this equation. The equation is flat out wrong. Why? Because a Fourier transform provides positive and negative frequencies. And here we have only positive ones. So where are the negatives? So this equation, sine, is not an equation sign. So I left out something. But on the first glance, when you see it, you say, yeah, that's what we are actually doing. And this is even not an equation. It's a jibber jabber, a wrong statement. And we're going now deep, and I'm going to uncover how actually the sine wave analysis is done, what is your instrument doing actually, and how it's done properly. And then we're going further to how we can do it with our noise signals. Yesterday, I was talking about the issues of the duration. We're going to touch this today also, because this is important. We cannot circumvent the issue of duration, but we can help a little with it. We went through multi-component signals, and this is where we are now. So now I'm going to talk about stochastic excitations. First, we have to generate it. We have to generate it properly. We have to double check whether what we generated is the true thing. And I'm going to give you all of these things. So what we said is, we have our system here. It has some frequency characteristics, and we would like to find it. And what I said here, the easiest way to do it is to find a signal, the input signal u of t, that has such a form that its Laplace transform is a constant 1. In such a case, this equation will become g of s equals y over s divided by 1. So if I use an excitation signal that has such a property, the output will be my ice. I don't need to use multiple excitations. I can use only one of them. So the question is there a real signal that has such Laplace transform? Yes, there is, and it's called a Dirac signal. This is a signal that has a spike around 0, and it's called delta t function. The thingy with this function is that integral from -infinity to +infinity delta t dt is 1. And this is a bizarre scenario. We have only one spike, and its area should be 1. So this means that this spike should be infinity high. We are becoming in a mind-boggling scenario. And this is called the impulse response of a system. So a response of a system on an impulse. So if we can generate such a signal, in reality, we don't need ice. We can just come and kick a system, and the output will be its transfer function. And that's why a lot of mechanical engineers, when they do testing, they hit stuff. When you hit it, it starts to ring out. The frequency that it rings out are the poles of the systems. Like when you play a guitar, every string has its own tension. And when I struck it, it starts to vibrate with its own resonance frequency. And we actually identify each of these systems. So when we struck a string of a guitar, we are calculating its ice just with a single strike. The idea is, can we do the same with electrochemical systems? Can we ping it and it will ring down its guts? Okay, we cannot do it electrically this correctly, but we can do it in a stochastic manner. So can we generate a random signal that has a flat spectrum? Let's do this. First thing, we have to, I will come back to this slide. This is a fundamental theorem in statistics, in stochastic processes, which is a subject called advanced statistical analysis, stochastic processes. It's a one-term exam in electrical engineering faculty, at least around Europe. The Wiener-Hintsching theorem states that the first bullet, the power spectral density of a random signal is a Fourier transform of its autocorrelation function. And now I could have speak in Slovenian. I think it might be exactly the same understandable as this in English. So let's see what the hell is this thing talking about. You have it here. You can go and check it. But I'm going to try to describe this in a comic book style approach. First, what an autocorrelation means. An autocorrelation is a measure to tell us if we are observing a signal at this moment, how much this information is going to help us to predict what will be the value of the signal in the next second. So in a context, if we have a sine wave, let's do it differently. If I have a straight line and I know it's a constant, and if I know its value here, what will be the value here? It will be exactly the same. So my current position here tells me enough information to predict the next step. Now let's go further. If I have a sine wave with some noise on top of it, and if I stand here, what will be the value of the signal in the next step? I can say that, okay, now I am at the top. It will most probably be a little bit down, plus minus some part. So I'm not pretty sure where it will be, but I'm not 100% sure where it will be, but it will be somewhere here. And I can go even further than this. If I take a white noise, if I stand here and I ask you what is the value of the next signal, of the next step, you have no idea, because the white noise is a random walk. This means that how you can do a random walk, it's like you are here, and in the next step you can jump from plus to minus infinity based on some distribution. So you actually don't know where you're going to jump. And if I draw the autocorrelation of such a function, it's like this. So if I'm at time 0 and I'm here, and I ask myself, do I know where the signal will be at time 0? I know it's here. So I said I know with probability 1 that it's here. Do I know where the signal will be in the next step? Because it can jump anywhere. In the next step, I know nothing about the signal. And what about in the previous step, where the signal was behind me? I have no idea. So white noise has this Dirac function. And we don't have to generate it infinitely long. We can just generate noise, and its autocorrelation is a Dirac. And if I do a Fourier transform of this, I get a flat spectrum. And this is the Wiener-Hintschen theorem. It says that I can generate a signal that has a flat spectrum. And in order for this to work, I have to have a Dirac signal, which I cannot generate. But because I'm not doing in the time domain, but I'm doing statistical wizardry, which is not, it's a formal mathematical concept, I can take a white noise and generate a signal that has a flat spectrum. And this is the main trick, the autocorrelation stuff. It might be mind-boggling to you, but this is the idea, what you have to think. If I stand at a point T, do I know where the signal will be in front of me or in the infinity? Can I predict it in front of me and where it was behind me if I just know the current value? That's the autocorrelation stuff. There is an additional thing called cross-correlation, which we are going to use also, but it's the same concept. It's not, it doesn't say about my signal, but it says, if I know that F is here, do I know where the G will be? Can I predict about the other one? It's not a situation that goes in both ways. So there is a cross correlation from F to G, and there is a different cross correlation from G to F. It doesn't mean that they're the same, because one signal might be more informative than the other. So it's not in both directions. So the trick here, our goal was, can we generate something that has a flat spectrum? And we know that in order to have a flat spectrum, we need to somehow come to Dirac impulse. The Dirac impulse, we cannot generate it enough, but we can generate noise whose autocorrelation is a Dirac, whose power spectral density is then flat. And we can generate white noise. We can generate white noise. So in order to so now let's go back. This is what I wanted. This is the final result. So we can generate white noise. This is what you have. You are in a digital age. This is really difficult for young people. If you go to a National Science Museum and take an old FM or AM radio or a TV with an analog antenna, I don't know if you can find it in Korea anyway, there is this like noisy stuff. Shh. This is a white noise. It has no information whatsoever. And this is the actual, you can generate this in whatever numerical software you're using. And if you calculate its autocorrelation function, it will be like this. So at time 0, I know where I am. But from time 0 onwards, I cannot predict anything. Neither if I turn my back, I don't know where I came from. I just know that I'm here. And if I calculate Fourier transform of this, I will get a flat spectrum. So this signal here contains all the frequencies from minus to plus infinity. This is all I need. And this comes from Wiener-Hintschen theorem, and what I provided you in these 3 slides without any mathematics, really crude and really imprecise, is almost half of a semester of advanced statistical processing in stochastic signals. If you have such a course or go on YouTube or whatever, check it. But this is all you need to know if you say, okay, I trust him. It seems logical. Okay? But the problem is the energy of a signal. So when we try to generate such a signal, we need to put some energy. The energy of a signal is actually the area under this curve. It's called this relation. It's called Parseval theorem. You can check it on Wikipedia. There is a derivation. This means that the integral from minus to plus infinity is infinite. It diverges. This means that in essence, if we want to generate such a signal, we need infinite amount of energy. And we don't have it. And now we boil down to a reality. What can we actually generate that resembles a flat spectrum? Because we don't have infinite energy. So now back to Wiener-Hintschen theorem, just a reminder, what does this mean? Let's generate this thingy. Now we said that we cannot generate white noise because it requires infinite amount of energy. But what we can generate is a signal that resembles white noise, at least to some extent. So I was talking yesterday about this telegraph signal, and there is this lambda parameter. This lambda parameter is important, but just to see how we can generate this, it's at every lambda seconds. This lambda can be really, really small, like a microsecond or a nanosecond or whatever, or 100 seconds. At every lambda second, we throw a coin. And we take a number from 0 to 1. If a number is bigger than 0.5, we flip the switch. If the number is below 0.5, we keep it where we are. So either we stay on +1 or we switch to -1. And we just go up, down, and that's it. There is a proper derivation from this signal. We can calculate its autocorrelation function. And if we take a Fourier transform of this, we can get its power spectral density. I'm not going to give you this derivation. You can find it. There is in the references, there is a reference to a book that is dedicated to this signal. You can find it. But what you can do is, when you generate this blue signal, you can actually calculate the blue line here, which is a numerical power spectral density. And the orange one is its theoretical one. So as you can see, the one thing that I generated here almost resembles the theoretical one. Why doesn't resemble ideally? Because I don't have infinitely long signal. If I take infinitely long signal, it will resemble, but we don't have infinite amount of time to do it. So that's why we make some mistakes, errors, which are acceptable. This lambda parameter actually determines where this 0 occurs. So if I want wider bandwidth, I should move this part this way. This means lambda should be increased. And if I want to generate lower bandwidth, lambda should be decreased. And by tuning this lambda, I can select the bandwidth where I want to excite my system. It might seem a little bit strange, but I'm going to show you a Python code how you can do it. Why is this now actually of practical use? This is of practical use because we can see this as if, imagine our white noise had a flat spectrum, plus minus infinity. But if we make a low pass filter here, we are actually generating a noise-like signal that is a white noise filtered out. And when we filter it out, we remove a large amount of energy, plus to minus infinity, and we have a finite energy signal. This means that we can generate this quite easily. Okay. This might be rather abstract. The takeaway note is the blue signal resembles white noise. It has all the frequencies up until certain bandwidth, which we can select by ourselves, and we can generate this easily. There is mathematics behind it. I just provide a simple glanced overview. You can go in deep and double check that what I've said is true. From an engineering perspective, all you need to do is this. So you have to specify the cutoff frequency. How wide frequency band do I want to excite my ice curve? This is connected to a sampling frequency. So because this is a digital signal, I have to sample it twice than the cutoff frequency. This is called Nyquist limit. If you don't know it, you can check it. It's a fundamental theorem. Why is this important? Imagine this. I'm going to come back to this on day 5 when we're going to do some practical stuff. If I have a sine signal with frequency 1 Hertz, I need 2 points to find it. So with just two points per second, I can recreate the signal. If I have a faster sine wave, so if I do it like this twice, and I sample, wait, let me do it properly. If I do it like this is twice. So if I sample the red ones here, 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 and here, I actually in the same time sample this, 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 and this. Sorry, and I sampled here and also here. So in order to sample the green one, I need 2 times more points. That's the basic idea. Otherwise, I cannot distinguish. If I sample only the red points, I cannot distinguish, is it the red signal or is it the green signal? Because both of them pass through these points. And this is the case where this Nyquist comes from. You have to sample twice as much as the frequency you would like to see. Otherwise, you cannot distinguish it. This is just a hands-on example, a comic book style. There is an actual theorem. It's called Nyquist-Shannon sampling theorem. You can look it up. It's really fine mathematics. And this is the comic book style representation of it. So next thing is, we would like the other most important part. So what we have is, we have the high frequency part. This is determined by our sampling frequency, Fs, and the low frequency part is determined by the duration of the signal. So when we generate our PRBS, discrete random binary signal, we have to determine the bandwidth. The bandwidth determines the sampling frequency, and the lowest frequency that we would like to estimate determines the duration. And again, what a lot of stuff. We're going step by step now through each and every point of this with Python and a lot of images. Let's generate it. So this is the algorithm for generating this signal, and it's really, really, really simple. In order to flip stuff one step at a time, we can flip 1,000 coins on our computer at once. So we decide how many points we would like to have in our signal. How can we decide it? We know its duration in seconds. So duration in seconds. We know its sampling frequency. So number of points is duration times sampling frequency gives us the number of points. So what we do, we generate n number, we take n coins and we flip them in a computer at the same time, and we get some heads, some tails, some heads, some tails. And then we decide heads mean +1, tails -1, or vice versa, it doesn't matter. And then we just split those coins up and down, and we generated such a signal. That's it. And we just say that between each flip, there is a time of lambda seconds. So we flip the coin, make lambda seconds, flip the coin, lambda seconds, and that's it. But we flip all n of them together. And this is the algorithm. The code is here. A really, really simple procedure. Let's go through it just to get an idea that is nothing special. So we have to first say the bandwidth of our signal. We would like to go up to n hertz, f hertz. So then we have to have sampling frequency. That is, sampling frequency should be bigger than 2 times f bandwidth. That is something what we have to generate. And this is the duration. we put these things together, and then we go. We say the actual bandwidth of the PRBS is 3 times this. Where does this come from? It comes from here. Let me remove this. Okay, I cannot. So it comes from here that this is the bandwidth that we desire, but the parameter is actually here, and this is 1/3, 3 times have bandwidth. It's from the derivation of the PRBS signal. You have to trust me on this one. You can check your derivation. And that is why we have this multiplication times 3. Then, as I wrote previously, we find how many data points we have, how many samples we need, and then we generate all these coins. We flip them all at once, and then just pack everything together in one array. That's it. Nothing special. Let's try this out. I think that I have a code here. Yes. Let's try this out. So for you can see it. It's notebook 2.1. So here in the notebook, you have everything written again. And what I'm going to generate here are actual signals that we are going to use in our excitation experiments. So I will generate a signal that has a bandwidth of 0.01 hertz, but because it's so low, I have to generate quite long signal. How do we decide how long the signal is? There is a rule of thumb. You need at least 5 to 7 periods of the lowest desired frequency. So in this case, the lowest desired frequency we usually take as a rule of thumb, I'm going to explain why, as a 10 times lower than this. So our frequency here is 0.01 hertz. That's the highest one. The lowest one will be 0.001 hertz. One period of that is 1,000 seconds. It's a really slow sine wave. And we need at least 5 of those. So we have to wait 5,000 seconds in order to have the lowest frequency. And this now exponentially dies down for 0.1 hertz, for 1 hertz, 10 hertz, 100 hertz. For 1,000 hertz, we are even in milliseconds, but we say, okay, generate 1 second signal, who cares? And if we sum this up, we need approximately 5,800 seconds to calculate ice from 0.001, so from 1 millihertz up to 1,000 hertz in 5,600 seconds. And you click it once, you leave it, and you come back and you have the ice. So let's generate this. So here I'm generating the signals, and here is how they look. So the x-axis are actually seconds, and which did I generate? I generated, yes, all of them, but I limit the duration to only first 10 half. So you can see the slowest one, just see the numbers here. These are seconds. So the first signal for the first 150 seconds, nothing occurred. It's flat line. And then we have one jump and then another, and so on and so on. And this will continue to 5,000 seconds. It will be slowly going up, down, nothing will happen. As we increase the bandwidth, the number of jumps and the duration of the jumps shortens. This is 60 seconds, and it has far more jumps. This is 20 seconds, more jumps, 3 seconds, and then we have 0.3 seconds, and the one that has bandwidth to 10 kilohertz, in 0.1 seconds, it has this, like beep, 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 beep. And this is the only thing what we have to generate, nothing else. With these 6 signals, we can calculate ice from 1 millihertz to 10 kilohertz with just these 6 signals. There is nothing more required. So I was telling you about all this mathematics, the bandwidth, I generate the signals. Are we sure that what we see here actually resembles the reality? Is the spectral characteristics of these signals the ones that I told you? Let's calculate this. So I'm going to take this, I'm going to start this. It will finish fast. Here it is. And then what I would like to do is, I'm going to do it like this. So what I'm doing here is I generate the PRBS, the DRBS signal with certain bandwidth, sampling frequency, and duration for all of these parameters. And how do I calculate the power spectral density? This is the theoretical one. If you see this, this relation is actually this one. Is actually this one. A squared lambda sinus x over x. Sinus x over x in Python is sinc. So this is the theoretical one. And how I calculate the numerical one. So I told you that the numerical one is a Fourier transform of the autocorrelation function. But in my code, there is nowhere FFT. This line is a crucial one, and it's called Welch. So it is really, really difficult to estimate the power spectral density directly through Wiener-Khinchin theorem. As I told you, calculate the autocorrelation, you can, and then take the Fourier transform of the autocorrelation, and this is where things start to break. That is why in statistical signal analysis, there are a lot of estimators of power spectral density. One of them is called Welch periodogram. I'm going to give you a link here. It's called Welch periodogram. And you can see it, how it goes. There are some references and stuff like that. It is a numerical method how to estimate power spectral density. It is a topic on itself. All of this stuff were invented in Bell Labs in the 60s, in the 20th century. And it's still one of the most commonly used algorithms. You can find it in any textbook. Go and look at it if you want. So this is that line that I'm showing here is the one where this is implemented. It's one line in Python. There is some theory behind it. You can check it. Now I'm asking you, trust me that this works. And this is how I do it. Okay. And now when we plot it, we are getting. So the first one had a bandwidth of 0.1 hertz. And we can see it, it has up to here. The second one had a bandwidth of, this one was 0.01. So it's 10 to the power of -2. The next signal had 0.1, and then it starts to fall. The third one had 1 hertz, and then it starts to fall. The fourth one has 10 hertz, 100 hertz, 1,000 hertz. And now the question is, but wait a moment, why do we need all of these signals when the last one has all the signals from almost 0 to 1,000? This one has from almost 0 to 100. And so if we would do it, we just need one of them. Take this signal, the fastest one, run it for 5,000 seconds, and you have everything. Yes, you can do this, but there are engineering issues with this approach. And this is what we're going to talk next. So you have a notebook here, how you can generate these signals and how you can double check, because you always have to double check that what you've generated is the actual thing, what we need, because we are generating noisy stuff. We have to double check what we are doing. Okay, so where we are now, so we covered the excitation signals, and now we are going to discuss the frequency bandwidth of those signals and some engineering aspects. And I think that when we finish this, the last column will be for after lunch stuff. Let's see how it will go. We have time. So, as I showed you, all of the signals that we generate have power spectral density from almost 0 to the bandwidth that we selected. This would mean, if I go down here, this would mean that, let me log in one more time so that I can scribble. This would mean that all I need is this signal, because the starting bandwidth is at all points the same. And since I want to estimate my eyes in this frequency, why am I dividing this like this? So the first one only captures this part, the second signal only this part, the third this one, the fourth this one, the fifth, and then the last one here. Why am I slicing this when the last signal contains everything? Well, as I told you, the high frequency part is determined by the sampling frequency, and the low frequency part is determined by duration. So what? We will take the highest frequency signal and we will wait for 5,000 seconds. So what? Well, we have an engineering problem. Just to get an idea of numbers. If we are here at 1 kilohertz, so this means that we have to have sampling frequency of 2 kilohertz. So I'm going to write 2,000 samples per second, -1. And we have to wait 5,000 seconds. So how many samples are we going to get? We're going to take 5,000 seconds times 2,000. And this is 5 times 2 times 10 to the power of 6. So this is 10 to the power of 7 samples. So what? 10 million samples. So what? Yes, we are measuring 24 bits. So we cannot, since we're measuring in bytes, that is, we have a, let's say, data acquisition with 24 bits. So we are practically measuring 32 bits. So this is times 8 bytes. And we are measuring maybe voltage and current. So this is times 2 at least. But if we have a stack of, let's say, 10 cells, we measure each cell separately plus the current. So this will become times 11. And if we start to multiply this, we suddenly reach tens of gigabytes of data. If you have this amount of storage, and if you can afford it, use just one excitation signal, generate 10 gigabytes of data and do whatever you want with it. But if you go in field, and if you tell a producer of, let's say, fuel cell systems, that in order to run the fuel cell, you need the 10 gigabytes of RAM, they will most probably tell you, okay, go out, forget about it. Okay, so that is why we are slicing this so that we sample only limited amount of numbers so that the memory is constant, so that you can go and say, oh, you need like 300 kilobytes of data and we can calculate everything. They will say, okay, 300 kilobytes, it's fine. So it might be a mind-boggling 2025, and I'm talking about kilobytes. If you take any instrument, what you have, most probably the instruments have 512 data points inside for signal generation. RAM is expensive still in industrial settings. So in laboratory, we can do whatever we want, but at one point you have to go outside of a laboratory, and this is why we are talking. So let's calculate this to find a sweet spot. This is the sweet spot that I'm talking about. This is how we use it. That's why we separate it like this. But we didn't come out with this setting as a rule of thumb. There is actual mathematics that provides us with this sweet spot. I'm going to describe it now. Back how we came up with this. So everything that I draw now, it's presented here in a more structured way. So the basic idea is to take the bandwidth that you would like to see and separate it in small chunks, low, high, low. So this should be low. No, it's like this, cutoff, n-1, and so on and so on. This would mean that we separate the bandwidth that we would like to, where we would like to calculate ice in small chunks. Why? Because here we have long duration, but small sampling frequency. And when we go to the next one, we have higher sample frequency, but a little bit lower duration. So the number of points that we are capturing is almost constant. Because at the highest frequency, we need to sample with 20 kilohertz, but we need to sample just 200 milliseconds. So 200 times 10 to the power minus 3 times 20 kilohertz. This cancels out, and we need only 4,000 samples. And we can capture that. If we go down, we are sampling 5,000 seconds, but we sample, let's say, with 1 hertz times 1, and we are 5,000 samples. So I'm constantly talking about really, really small amount of samples. In such a way, we don't need huge, in the implementation, we don't need direct memory access. We don't have to FPGAs to calculate everything. We are talking about small number of samples. So this is a point where we are leaving a laboratory and going to a real world implementation. You cannot ask a car. How we came up with this? We went to a car manufacturer in Slovenia that makes battery management systems for, is a tier 1 producer. And we were explaining this, and he asked us, what's the price of, how much is it? And we were discussing production costs, and it was some technical director, and he said, like, okay, just to give you an example, where is your time frame? And he took out from his wallet a euro cent. A euro cent is 100 wons or 10 wons? 1 euro is 100 and 1,500. Yes. So 100 wons or 10 wons, zeros. And he said, this amount of money is infinite amount of money in car industry. If you pass or outside of, let's say, 100 wons, you are infinite amount of expensive. You have to do it below this, and you have to do all of it. And that's, for that amount of money, you have to start to calculate the bits. Otherwise, you immediately jump above 100 wons. And when you start calculating bits, this is where you come up with. So where is the sweet spot? Because we can take 2 decades, 1 decade, 1.5. Where is the sweet spot? You can actually calculate this. This is the mathematics inside. What is when we calculate this equation, this graph up here comes out. So the sweet spot is to divide the bandwidth into 14. Like 14 decades. And we said, okay, let's divide it person by 10 because it's easier. So every decade, its own sampling frequency. So there is in such a scenario, you will use only 0.004% of the memory instead of sampling everything with just one PRBS curve. So if you slice it like that, you have almost 100% savings in memory. And this is where you come down to 100 wons limits. If you are in a laboratory and you have all the money and time in the world, in quotation marks, you can just use this one, take it, generate a gigabyte of data, forget about this. That's why I was generating 6 PRBSs, since we limit the amount of data, it complicates a little bit. So you have to generate the first one, make an excitation measure, generate the second one, excitation measure. So you have to repeat this measurement 6 times, but the amount of data is practically nothing. You save tons of space and time just by doing this trick. Okay, so that is why we are seemingly complicating it like this, and that's why we say that the useful bandwidth, if the bandwidth of the signal is FB, the useful bandwidth is down to FB divided by 10. That's it. The optimal value would be FB divided by 14. But 14, it's a strange number. Let's do it by 10. We are a little bit suboptimal, but who cares? We saved almost 99.99% of memory anyway. So now that's why we do it like this. Okay. So now we discussed the signals, we discussed the frequency bandwidth and the money, or once, is it like this, the signal, the symbol? We discussed this. While you're doing this, we calculated all the bits, the bytes and everything. Now we have an excitation signal. So if I go back to the first slide, then I'll jump back. Sorry for. So now we generated this. We have 6 such signals, and I explained why we have 6. We will run them through the system, and we will get 6 outputs. This is where we are. And now we have to use these 6 inputs and 6 outputs to calculate our impedance. So let's do it. Okay, in order to do this, we are not talking anymore about Fourier transform. We cannot talk about it anymore, because stochastic signals, when I draw here that it has a flat spectrum like this, this doesn't mean that all frequencies are present all the time, because if they were all present in the same time, there will be huge amount of energy. Some are present now, some are present later. On average, they're present. This means that we cannot just take FFT and calculate everything. We have to slice the signal during time, because at some time points we have excitation and then we don't have, and don't have. And we don't know where these times are. It doesn't mean that when it goes up, we have to sample, and it goes down, we don't. These things are not the same. So in order to analyze it, this is where we come to a concept of advanced signal processing. First case scenario is a really simple concept. It's called short time Fourier transform. If you take a course of advanced signal processing, these slides are the first 2 months. So I'm going to do it in a comic book style. If there are any mathematicians or electrical engineers, I hope that your ears will not shed any blood. This is now crude and the really direct way of talking about this comic book style. The idea is this. We have a signal, and instead of calculating Fourier transform on all of it at once, we start slicing the signal with a window function. So we take only this part and calculate Fourier transform, and we get one line here. And then move the window and another slice and cut it here. And now there is a whole theory. What kind of window should we use? What kind of overlap? How should we move it? What's the length of the window? I'm not talking about anything of this here. And if we do it over and over and over again, we can generate figure like this. What this figure shows is that this frequency here is present up to here, then there is some wiggle here, and then it's present all the way here, then it's lost, present, lost, present. In the same time, there is another frequency that is constant, another component that is constantly changing. So we have a signal that has one constant frequency and one like when a train goes by and you see this Doppler like wee, those kind of, and you can see it in the time domain. It has some high frequency part and then it slows down. And if you do this slicing FFT, you can see that we have one constant and one slowing frequency down. And this is the thing what we would like to do. In such a way, in a frequency, if you do a FFT, you will get that there is a, so if I write it, if I make a sketch, if we have something like this and do a sine wave, and I do this, and then I do FFT of this signal, I'm going to get, I guess, something like this, a peak at this frequency. And the Fourier transform will tell me that this frequency is present in the signal. It doesn't tell me whether it is present all the time or it is just localized and where it is localized. So instead of having just frequency information, I want time and frequency. I want to ask which frequency was present in which time in my signal. And this is called short time Fourier transform. And it's the first step in doing time frequency analysis. There are problems with resolution and another particular numerical issues with this. So between this short time Fourier transform and what I'm going to show on the next slide, there was quite a lot of development in the 20th century. Currently, the best way how to analyze this signal is called a wavelet transform. And what is the core idea? When we choose a window in our short time Fourier transform, we select the time frequency resolution. What does it mean? Because I have, this is my signal T and I have something here, whatever it is, and then I select some kind of window. And when I do FFT here, all I can say is that this frequency occurred somewhere within this delta T. I don't know where exactly in this delta T, but I know that is within here. And that's why we have here this grid. And by selecting the width of the window, we immediately select the width in frequency. It is the same concept as Heisenberg principle of uncertainty. You cannot get infinite time frequency versus infinite time resolution versus infinite frequency resolution. There is a trade-off. The area of this rectangle is constant. So if I stretch it in time, I will lose it in frequency and vice versa. And wavelet transform actually does this. Instead of having flat grid like here, we have adaptable grid. So signals that are really slow with long duration are having really, really fine frequency resolution, but really bad time resolution. As the frequency increases, we have really good time resolution. We can see whether spikes occurred, but we don't have a frequency resolution that good enough. But this adaptability is something that what we are going to exploit in the next couple of slides. So how to get this idea in your head and why are we doing this? So let's discuss first something that is, this is now called, the area is called multi-resolution analysis. There is a book by Stefan Mallat, is approximately 800 pages long to describe why this works. And I'm going to do it comic book style on this slide. So the idea is the following. We would like to generate something that is called orthogonal space. And now I'm starting to speak Greek. Let's do it comic book style. An orthogonal space, what the hell is orthogonal space? All of us know what an Euclidean space is. It's a graph that has X and Y, or we can have a Z for three-dimensional, and this is what we see. And why is this space called orthogonal? How can we define this space? Well, we can define it by two vectors. A vector of length 1, whatever it is, 1 meter, 1 centimeter, length 1, that is X vector, and we have vector Y that is perpendicular to this vector. And with these two vectors, we can access every point in this space. Go this much on X and this much on Y, and you can get to this point. So this is quite clear. Everyone is nodding, right? But who says that these vectors must be straight lines? So how do we know that these two vectors are perpendicular to each other? What is the measure that we can use to find that the two vectors are perpendicular? It's called scalar vector product, or we would like to calculate the cosine between these two vectors. If the cosine is 0, then they're perpendicular. And everyone is nodding, that's logical. Who says that we have to have straight lines? Do we know another two functions that are perpendicular to each other? Yes, we do. And you will nod again. We have a sine signal, and then we can have a cosine signal. What is the phase difference between sine and a cosine? Is 90 degrees. So instead of having straight lines, let's imagine, and now this is an LSD domain. Let's imagine a space where x-axis is a sine wave and y-axis is a cosine wave. Is this an orthogonal space? We're going to say, what is the length of a single sine period? It's 1. What is the length of a single cosine period? It's again 1, so okay. What is the phase difference between these two? It's a p-half, so it's an orthogonal space. So how do we call this orthogonal space where we have one sine and one cosine? We call it a Fourier transform. So now you are all nodding. So now we have a sine and cosine space. But who says that it should be sine and cosine? We can discover a gazillion different functions that have these kind of properties. And one of those functions are these wavelets. So this is not immediately visible. Now you have to, this is where the half of the book is present. Now I cannot explain it this simple, but now you have to trust me that these wavelets are really such functions that generate such an orthogonal space. And why this orthogonality is important? This means that we can separate a signal in time and frequency in such a way that if we sum it up, we get the whole signal. Nothing is doubled, nothing is lost. How we can imagine the wavelet transform in a more comic book style approach? If you see these wavelets in this middle picture, they're like wavy thingy, and they're concentrated in time. They're not infinite. After a certain point, they're 0. So what we do with these wavelets? The wiggly part in the wavelet determines its frequency, like sine and cosine. We'll see how it determines. And what we actually do is we can take this wavelet and we can stretch it out. If we stretch it out, its frequency decreases. If we compress it, its frequency increases. So what we do is we stretch it and stamp it on our signal. And by doing so, we are taking out low frequency parts. And because we stretched it, that's why we are stamping it here. It's stretched. And if I want to find the high frequency part, I compressed it and I stamp my signal and I immediately get the high frequency part because I can stamp it. And how am I doing this stamping up and down? By this integral. This is what this integral does. Stretch it, stem, 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 compress it, stem, 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 and we actually calculate all of these points slowly. So I stretch it the maximum, 1, 2 stems. Compress it, 1, 2, 3, 4. Compress it one more time, tsk, tsk, tsk. And I do this, and this integral actually does this thing. And what we get is an orthogonal space. So when I do this stamping, I decomposed my signal into a time and frequency space that is orthogonal. So this means that if I sum up all these stems, I will recreate my signal back. This is the important part. So comic book style wavelet transform without any mathematics. Wait, this is all that I was talking about. So the things how we do compression and move around is by these two parameters, U and S. Parameter U moves the signal, moves this stamp in time, and parameter S compresses it or stretches it out. And this is how we do the wavelet transform.